Okay, good morning. Today we're going to continue with our discussion of chemical bonding, chapter 8. And so we talked about this octet rule and how elements or how atoms are somehow stable when they contain 8 valence electrons. So that plays out in ionic bonding at times, but it also plays out in covalent bonding where electrons are shared. Now, what we're going to start with today is a discussion of what's called electronegativity. And electronegativity is going to allow us to describe how some covalent bonds have a particular property called polarity, bond polarity. And we'll take a look at that first. So the beginning of electronegativity is section 8.4. So it's section 8.4, which is electronegativity. And polarity. And one reason that we're concerned with this issue is that it turns out there's some molecules. So for example, if I take the HF molecule, those two atoms we believe are covalently bonded to each other. Remember, the line notation is a pair of electrons that are shared between the two atoms. Okay, we refer to this as a single bond. And it is covalent. Although it's an interesting bond. It turns out if you study this molecule, you will find that it has a small negative charge near the fluorine atom and a small positive charge near the hydrogen atom. Small, we're going to use the symbol delta. Greek letter delta, which means small. Okay, so there's a charge on each of these atoms, opposite charges. And in fact, the amount of positive charge is equal to the amount of negative charge. So they cancel each other. So overall, the molecule is neutral. You know, like when I say cancel, what I mean is imagine I said, you know, -1 and +1, they cancel each other, right? They add up to 0. So it turns out if you start studying these charges on HF, the amount of charge on the hydrogen is around 0.4. So an electron has a charge of -1 and a proton has a charge of +1. So on the hydrogen, you have a positive charge of about 4/10 of a unit charge, 4/10 of the charge of a proton. And on the fluorine atom, the charge is around -0.4. Okay, so they cancel each other, right? But there are charges, and they're, you know, because they're less than 1 unit, we call them delta, meaning small. Okay. So notice delta is used in different meanings in chemistry. So the uppercase delta is used for changes, right? And then the lowercase delta is meant for small. Okay, and so in this context, it's just small. So the way that we explain this phenomenon, that this molecule has electrical charges on it, which can be measured and studied, has to do with electronegativity. Okay, it is a property of an atom. Atoms have a property called electronegativity. And we give credit to Linus Pauling, who back in the 1930s worked on this issue. And we'll look at what, in a moment, we'll look at what's called an electronegativity chart. And it's often referred to as the Pauling electronegativity chart based on his work with that science, okay? Essentially, Pauling, the way we can phrase it today, and this is not technically what he said, but we can look at it from our perspective, is saying the following. Imagine you have two atoms which are sharing electrons. And typically when they're sharing electrons, they're sharing pairs of electrons. So either 2 electrons or 4 electrons or 6 electrons. There are 1 electron bonds and 3 electron bonds, but we're not going to worry about those. It's typically pairs of electrons. If those atoms are different elements, so for example, A could be hydrogen and B could be fluorine, or A could be oxygen and B could be lithium, you know. If they are different elements, they have a different value of electronegativity. So electronegativity is a value, there's a number we're going to associate with it. And I'm not going to go through how it's calculated and how it's measured. It's a pretty involved issue, but we'll look at the actual values of what they are. So there's some property called electronegativity. You can think of it in the sense that, you know, each element has a density, right? Each element has a specific heat capacity. Each element has a color, right? Like each element has certain properties that describe that element. And so electronegativity is one of them. But electronegativity plays out in chemical bonding in the following way. The greater the electronegativity of an element, the more it has a tendency to hold or withdraw the electrons in a bond toward itself, okay? So electronegativity is all, for us, it has to do with these electrons in here. What are these electrons? How are they going to behave? And it turns out that if, I'm just going to arbitrarily say that B has a higher electronegativity. So I'm just going to say that this one has a higher, and let me abbreviate electronegativity because it's a pretty big word, higher electronegativity. And let's say that atom A, has a lower electronegativity, right? Higher and lower. If that is the case, what will happen is these 2 electrons will be withdrawn toward the element B, towards the atom B. And as a result of that, B will now have excess negative charge and A will have excess positive charge, right? You know, if you are losing some electron density, you're going to become more positive. If you gain some electron density, you're going to be more negative. Now let's think of it in terms of orbitals, right? Orbital theory. If we drew it like that, you know, we could draw an orbital. I'm going to draw an orbital like this. So let's say that we have this orbital and it's, you know, symmetrically distributed around the 2 atoms, right? Okay. In fact, let me change it a little bit. I'm going to make it even a little more accurate. So here's atom A and here's atom B. Let's say that this orbital looks something like this. It actually surrounds the nuclei of both atoms. Okay. So this is the orbital. This is the atomic, or I'm not going to call it an atomic orbital. We'll call it an orbital. Okay. Now, if B has a higher electronegativity, what's going to happen? You're going to get more electron density around B. So you have more of the orbital around B and less of the orbital around A. Remember, it's a wave, right? So now you have higher electron, you know, more electron, I'll call it density, and less electron density. Okay, and what will happen is you'll get a negative charge here, and you'll get a positive charge there. So This is, you know, maybe a nicer way to show it because you're using something that's pretty real, like an atomic orbital, in order to describe what's happening in terms of the electrons, okay? So the electronegativity plays out when it becomes important when there's a covalent bond between two atoms, okay? Now, the higher the electronegativity, that's the element that's going to have the negative charge. The lower the electronegativity, that's the element, the atom, that's going to have the positive charge, okay? What happens if they have about the same electronegativity? What if they're about the same? Like you can have two elements with about the same. Then what happens is they share the electrons equally, and it kind of looks like a regular, you know, covalent bond, and there is no polarity, okay? Now, there are no two elements that have exactly the same electronegativity, but there are elements that have pretty close to each other, close enough that we would say, yeah, they're about the same, okay? So what I'm gonna do is I'm gonna show you now a table of electronegativities. These are the Pauling electronegativities. Here we go. Nice, I found this one online. Electronegativity. And what I want to do is I want to start off way over here on the left. Let's start at the top left with hydrogen. Hydrogen has a value somewhere around 2. And 2 is kind of an intermediate value. Notice that the metals below it are much lower, you know, less than half. So it jumps down to 1 and then 0.9 and then 0.8. I notice there's commas in there, so this is probably European. But it's 1.0, 0.9, so forth and so on. But notice these elements are all pretty close to each other. They're a little different, right? They differ. I mean, 1 and 7.7, that's a 30% difference. So there's some difference there. But hydrogen is much higher, okay? And then as you move to the next column over, you get a pattern, which is as you move down, it decreases. So beryllium is 1.6, magnesium is 1.2, calcium 1.0. The differences become smaller and smaller, but in general, it's decreasing. Same thing here. As you go down, it decreases. That's a pattern you should be aware of, okay? There's another pattern, which is that as you move to the right, it increases. Okay, now they're using some color coding here. If something is red, that means it's got a very high value. If it's green, it has a low value. And if it's in the between, it has a yellow value, yellow, orange, whatever. Okay, so the highest values are, you know, pink and red over here. Kind of like that. It's nice color coding. Okay, so nitrogen, oxygen, fluorine, and chlorine. Those 4 have the highest values. Fluorine is the highest at 4.0. There are no values in this table. Sometimes they will put values in the noble gases, particularly for xenon and krypton, because those 2 elements can, in fact, form bonds with oxygen or fluorine. So they sometimes have values, but they're unimportant for us, okay? So notice same pattern, decreases within a family, right? This is called a family. It decreases within a family, decreases within a family, increases as you move across from left to right. So the highest values are up here and the lowest values are over here. We are primarily just concerned with the first 2 columns, especially hydrogen, and then the non-metals and the metalloids. So like these elements over here, those are the ones we're concerned with because we're talking about covalent bonding. These elements can undergo a type of bonding called metallic bonding and another type of bonding which is related to covalent bonding, but it ends up being a pretty complex issue. So we don't really worry about those too much. So just focus mainly on these. Now, what I do is I memorize some of them. I memorize, you know, hydrogen 2.1, lithium 1, and then sometimes this appears as 1.5, not 1.6. So they're not exactly the same in every table. So I remember it this way: 1, 1.5, 2, 2.53, 3.54. And so that's a pretty easy pattern, right? Just increases by a half each element over, all the way to fluorine. Fluorine being the highest, okay? Oxygen, the second highest. Those are the most electronegative elements. So you know, if I were to compare, I would say, oh, this one's going to be lower down here, polonium, because it's further down than oxygen. They tend to move up over here. So if you were going to compare cesium, that would be very low. Fluorine would be very high. And so you can make all those comparisons. Okay. So let's take a look at a couple of problems on Alex. So the first one I want to look at. Oops. Okay, there's your chart. And here's the first one. So reorder each of the elements in the table below if necessary, so that the elements are listed in the order of decreasing electronegativity. So decreasing, you want to go smaller, smaller, smaller. Okay. So pretty simple. Like these three right here are all in the same family. Oxygen is above sulfur, which is above selenium. So what happens is if you're going in decreasing, that means you're going from larger to smaller. So the largest would be oxygen because it's up at the top. The next largest would be sulfur because it's second. It's right underneath oxygen. And then selenium is going to be the smallest because it's below sulfur. So the order would be oxygen, then sulfur, then selenium. Now, if we look at these three elements, they're not in the same family. Boron is it's in 3A, group 3A. Fluorine is in group 7A, and then nitrogen is in group 5A. But they're in the same row, they're in the same period. So that means they're going to increase as you move from left to right. So the largest would be fluorine because it's the furthest over to the right. Nitrogen would be next, it'd be smaller because it's, you know, to the left of fluorine. And then boron would be the smallest because it's all, you know, it's even further up. It's in group 3A, right? You can just go back to that chart and look at it. It increases as you move to the right. So fluorine, then nitrogen, then boron. Boron would be the smallest, okay? So that particular problem is pretty straightforward. It's just looking at the table and deciding which one is higher, which one is lower, and which one's in between. Okay. Next, we look at predicting bond polarity. In each of the molecules drawn below, so there, notice they highlighted these bonds with red lines, right? By the way, if you have one line, that's one pair of electrons, that's called a single bond. If you have two lines between two atoms, that's called a double bond. Two pairs of electrons is a double bond. And if you have three pairs, that's called a triple bond. So the first molecule, CLF, has a single bond. The second molecule, N2, has a triple bond. And then the third molecule, CO2, has a double bond. Two double bonds, in fact, right? In each of them, the chemical bond is colored in red, or is colored red. Decide whether the bond is likely to be polar or not. If the bond is likely to be polar, write down the chemical symbol for the atom that will be more negative, right? The more negative is the one that has the higher value of electronegativity. So let's look at the first one. First one is CLF. Chlorine is 3.0 and fluorine is 4.0. That's a difference, right? There's definitely a difference between those two elements. So that's a pretty big difference, actually, 1.0. So fluorine would be negative, chlorine would be positive, and yes, it would be a polar bond. The second one is N2. Now, those are the same elements, right? So they both have the same electronegativity. So there's no difference at all, right? This is exactly the same electronegativity. There's no difference. So that would not be a polar bond at all. The third one, the red bond, the double bond, is between carbon and oxygen. Oxygen is 3.5, carbon is 2.5. Again, there is a difference there. So a difference of 1.0, right? So that would be a polar bond, and the more electronegative atom is the oxygen, 3.5, so it would be negative. The more electropositive element would be the carbon, it would be positive, okay? So that would be a polar bond. So we call them polar or polar covalent. Nitrogen is not polar covalent, it is just purely a covalent bond, equal sharing of the electrons, no charges on the atoms, okay? Now, in general, it's a little tricky, but in general, what you do is you say if the difference in electronegativity values between the atoms is less than 0.4, then we say that it's nonpolar. So even if there is a little bit of a difference, like 0.2 or 0.3, we would say that it's nonpolar, or you could just say it's covalent. Different textbooks will use different terminology here, slightly varied, but if it's greater than 0.4, or I'm sorry, greater than or equal to 0.4, but less than 2, okay? Oops, sorry. Okay. I'm sorry, I'm not really drawing that way. Drawing that well. Sometimes I have to be more explicit about this. So it's less than 2, but greater than or equal to 0.4. So that's a little easier for me to write it that way. So if the difference in electronegativity is greater than or equal to 0.4, but less than 2, then we would say it's polar or polar covalent. Okay? So if it's less than 0.4, it's nonpolar or just covalent. If it's between 0.4 and 2, it's polar or polar covalent. And then if it's 2 or greater than, so if the difference in electronegativity is greater than or equal to 2, then it's actually considered an ionic bond. So it's ionic. So I guess maybe for this top one, I'll write it using the same format. So if the difference in electronegativity is less than 0.4, there we go, right? That makes more sense. Okay. Nonpolar. So you have nonpolar, polar, and then ionic. So it's an interesting issue, right? So for example, if I have sodium fluoride, you know, we see, you can see that's a metal with a nonmetal. We've always said that that's an ionic compound. Well, it actually works out in terms of the electronegativity in our chart here, because sodium is 0.9 and fluorine is 4.0. So the difference in electronegativity is 3.1. Well, that's way over 2. So we would say it's an ionic bond. And in fact, it's not even really sharing electrons. It's actually a positive charge and a negative charge. So electronegativity is a pretty useful idea for thinking about the polarity of these bonds. Okay, we'll come back actually a little bit in chapter 9. There's another use of electronegativity that has to do with Lewis structures. And it's connected to this issue of what we call formal charge calculation. So we'll look at that a little bit later. We'll either get to that today or tomorrow. And so formal charge electronegativity is an issue. Okay. All right. So let's do this. The next issue is section 8.5, which is called drawing Lewis structures. Okay. Okay, so we're going to go through drawing Lewis structures. And when we're drawing Lewis structures, the idea is this. You're gonna start off with a formula. Like I'm just gonna start with water. We'll start with water. So here's water, H2O. Here's a useful way to think about it. What you do is you look at the chemical formula and see how there's 2 hydrogens and 1 oxygen. The element that there's only 1 atom, so that'd be oxygen, you put it at the center. Okay, so that's your first step. That's called a central atom. We're going to call oxygen the central atom. So it turns out molecules kind of grow like trees. You know how a tree has a trunk and then it has branches? And then those branches have smaller branches, and then those smaller branches have leaves. Okay. Similar thing happens in terms of the formation of molecules, which kind of makes sense since you think about it, a tree is made of molecules. So there's some symmetry in that. The other element, the one there's more than 1, what you do is you draw 1 line and then put those elements just around the central atom, and we call them surrounding atoms. So this would be a surrounding atom, as would this one as well. Those are called surrounding atoms. Now, if you only have 1 surrounding atom, it's not really surrounding, so you just draw them next to each other. So for example, if I had OH, you would just put OH. Right? Okay. Now remember, this line means that you have 2 electrons, right? That's our Lewis structure notation for a pair of electrons. So for that reason, we're going to take that into account. Okay. So step 1, you draw, this is called the skeletal arrangement. H2O. You have the oxygen at the center, and then it has 2 surrounding hydrogens. Okay. Think of the central atom kind of like a box, like we did with the Lewis dot symbols. You know, you're going to have a box. So you have the potential there for 4 surrounding atoms. Okay. Now, if there's more than 4 surrounding atoms, so for example, if I have a xenon atom, then it's actually useful to kind of think of it sort of like this: 1, 2, 3, 4, 5, 6. So if you have up to 6 surrounding atoms, you know, these are your surrounding atoms here. You can do it like that. If you only have 4, then you can do it like this. Okay, so central, surrounding, central, surrounding. Okay, so now we're at this stage where we've got this water. Now you do some counting, and this is the tricky part for a lot of people. What you do is you go to your periodic table. So hydrogen is in group 1A, right? So that means it has 1 valence electron. Oxygen is all the way over here on the right side of the periodic table. It's in group 6A. So that means that it has 6 valence electrons. So don't use the 8, use the 6. So now each of these atoms has a certain number of valence electrons. Again, I'm getting that from their position in the periodic table. And you add them. So that's going to give you 8 valence electrons. Right? So when you build these molecules, what you're doing is you're just adding up the electrons that are in the periodic table, the number of valence electrons, and you're going to use them to form bonds and lone pairs. Okay, so now here's the thing though. We've already drawn in a bond between the oxygen and each hydrogen. So that's 4 electrons that we've already used, right? 2 electrons per bond. Now, why did we do that? We did that because they have to have a bond. They have to have at least 1 bond. You cannot have a molecule with no bonds. It wouldn't be a molecule. They would be separate atoms. right? So there's got to be at least one bond. So we made that assumption. So I'm going to subtract 4 electrons that were already distributed. And that leaves us with 4 remaining electrons. We have to distribute somewhere the 4 that we didn't use here, okay? We're not gaining or losing electrons. We're going to keep the same number. So the question is, where do they go? And this is where the octet rule comes into play. Remember, the octet rule says that many of these elements are stable with 8 electrons, not 6, not 5, not 7, but 8. Hydrogen, however, has its own specific rule, which is called the Duet Rule. Hydrogen only needs 2. So it's already got 2. So it's already done. But oxygen needs 8. Well, so this is what you do. You distribute them as lone pairs on oxygen. Okay? So now the oxygen has 8 electrons. That's the octet rule. And hydrogen has 2. That's the Duet rule. And that's essentially what happens. It turns out that's not a bad model for what the water molecule looks like. We can use that kind of picture of water for all sorts of different aspects of chemistry, the reactivity, the physical properties, all, it builds into a lot of different ideas. And this is called the Lewis structure. Lewis structure is driven by octet rule, Duet rule for hydrogen, pairs of electrons. There is evidence that these are all pairs of electrons. And some are bonding, some are non-bonding. Remember, the ones that are non-bonding, the 2 pairs on oxygen, are called lone pairs. So there's 2 lone pairs on oxygen. Okay, so it's pretty straightforward. You draw the skeleton. You count up the number of valence electrons. You subtract the ones that you've already drawn in, and then you distribute the remaining electrons onto the atom that needs 8. Okay. So hydrogen is never going to have more than 2. So let's try another example. Now I'm going to show you one that's exactly from Alex. How many valence electrons are in the phosphorus tribromide molecule PBr3? Now that's a really simple question. All they're asking you to do is count up the valence electrons. So that's just one of our steps. But I'm going to go through the whole thing here. I'm going to go through this whole process so that you can see examples of how to draw Lewis structures. The goal of this whole thing is drawing Lewis structures. Organic chemists, that's what they do. They draw Lewis structures and then they think about the chemistry that might happen. But it starts with the Lewis structure, okay? So the molecule is PBr3, or phosphorus tribromide. So let's try to draw the Lewis structure of PBr3. In that, we'll find the number of valence electrons. Okay, so the first thing you do is you draw the skeleton. So you put a phosphorus at the center. Why phosphorus? There's only one of them, so it's the central atom. And then you think of corners in a box. You put the bromine atoms around that. There's your skeleton, right? We call that the skeleton. For some reason, SK doesn't seem right, but that is how you spell it, right? Then you count your valence electrons. So phosphorus is in group 5A, bromine is in group 7A. So the number of valence electrons would be 5. And then there's 3 bromines, so 3 times 7, 26, okay? Now, let's go on and let's do the next step, which is to draw the structure. So what I'm going to do is redraw the skeleton. How many have we used? You have 1 bond between the phosphorus and each bromine, so that's 6 electrons, 2, 4, 6. So we've already used 6, so that leaves us down to 20. So here's what I would recommend doing. Obviously there's no hydrogen in here. If it's hydrogen, you don't need to add any electrons to hydrogen. But for any other element, you're going to use the octet rule. So bromine, you're going to use the octet rule. Phosphorus, you're going to use the octet rule. So here's what I would do. Draw in pairs around each surrounding atom first. Don't do the central first, do the surrounding, till there's a total of 8. So you see that bromine on the left there, it has 8 because it's got 3 lone pairs, which is 6, plus a bond, which is 2. So 6 plus 2 is 8. And you just go around until you run out of electrons. Get them all up to 8. So what I've done is I've just put in 18, right? 6, 6, 6 is 18. I still have 2 to go. Where do I put them? I'm not going to put them on the bromine because the bromines all have 8. Put it on phosphorus. And now I've used all 20. And a lot of molecules are that simple. You just put 3 lone pairs on the surrounding atoms and then 1 lone pair on the central, or 2 lone pairs on the surrounding, or 1 lone pair on the surrounding. Depends on the element. Very often it's 3 lone pairs, but you just don't add more electrons than you have though, right? Like if I had 18, I wouldn't add 20. You got to stop when you run out of electrons. So I've used 20 and we're done. And each of these is octet. Most elements are octet. Hydrogen is the duet. We're going to look at some exceptions a little later. Probably do that either tomorrow or Wednesday. But for right now, these compounds are, and ions are going to use the octet rule. Okay? Let's look at another example. Okay, I'm going to show a harder one now. What makes this one harder, the Alex question is easy because it's just asking you for the number of electrons, the number of valence electrons. That's actually easy. But the question is how you draw a Lewis structure. So I'm going to bring your attention to the carbon atom. This is called an organic compound because it has carbon and hydrogen. When that's the case, what you do is I would just underline the carbon, just identify where it is. And the carbon is going to be the central atom. When you see HC or H2C or H3C, just attach it to the carbon. Okay, so HC. Then if you see oxygens, if there's more than one oxygen, attach them separately to the carbon. Okay, like that. Okay, so if it said HCOH, you would put HCO, and then the H is going to go on one of the hydrogens. Oops, sorry, one of the oxygens. I said that completely wrong, didn't I? The H is going to go on one of the, it doesn't matter which one you put it on. Okay, and that is a very common pattern. So HCOOH, HCOOH. Okay, carbon is the central atom. Technically, this oxygen is too, because it's attached to more than one atom. This one is not, but there's really 2 central atoms there. Okay, carbon is sort of like the trunk. So like if well, I'm not even going to show pictures, but when you draw these structures, put the carbon at the center. It's the trunk. Okay. Now let's do the question, which was how many valence electrons? Hydrogen is in group 1A, carbon is in group 4A, oxygen is in group 6A. So you just add up the electrons. 1, 4, 6, 6, 1. So valence electrons is, so I'll write it, valence electrons is 1 plus 4 plus 6 plus 6 plus 1. I think that's 18. Let me see. 1 plus 4 is 5. Plus 6 is 11, plus 6 is 17, plus 1 is 18. So 18 valence electrons. How many have we drawn? 8. We've already used 8. Okay, so 18 valence electrons, but 8 have already been used. Remember, a bond is 2. Now, like I said before, hydrogen is only going to have 2, so don't worry about hydrogen. But all the other elements need to have 8. Carbon, oxygen, chlorine, fluorine, bromine. 8 for all of those. So what do? Well, do the surrounding atoms first, and if you still have electrons, put them on the central atom. Okay, so there's 6. So I'm down to 4. I've run out, right? I'm done. And the carbon still only has 6. So we have an interesting situation here. Oxygen has 8. Octet. Hydrogen has 2, duet, but carbon only has 6. So what do? Pick the surrounding atom that's attached to the carbon that has the most lone pairs. See how this one here has 3 lone pairs? This one only has 2. Pick the element that has the most lone pairs, and this is a new idea. What I'm going to do is called electron pushing. And I want to try to draw this correctly so that my colleagues in organic chemistry, when you take classes from them, they don't get upset. I'm going to push this pair from the oxygen as a lone pair toward the carbon so that it's shared. So see where I'm drawing that arrow? That's called curved arrow notation. That pair of electrons is now being pushed so that it is shared equally between those 2 atoms. And that's then represented with a double arrow. That double arrow is telling you we're going to have a new Lewis structure. That new Lewis structure, I'm going to draw the rest of the molecule first. There we go. We now have a double bond. And that's called electron pushing. And now what we've done is we've made it so that all of those atoms now have 8. See, this oxygen still has 8 because it's got 2 pairs shared and 2 lone pairs. So the one that has 8, that's the one you're going to push a pair over to give the other atom an extra 2 because they both get to count them. So this now has 2, this one now has 8, this one still has 8, this one still has 2, and this one still has 8, right? And that's what you're looking for. Octet rule for all the elements except for hydrogen, and you're set. There's your Lewis structures. So there's your technique, right? Draw the skeleton. That's a little tricky because of the organic nature of the molecule. It wasn't obvious how to arrange the atoms, but that's how you do it. You put the carbon at the center, surround it with any hydrogen that comes before it. You're going to put that on that carbon. These are both going to be surrounding oxygen. So both those oxygens go on the carbon. Take your remaining electrons, distribute them around the surrounding atoms first. Often with carbon, you then don't have enough. So then you take the atom that has the most lone pairs, the greatest number of lone pairs, and you push a pair over to it so that both those atoms can share those electrons and they both now have 8. This is the octet rule, and this seems to be a driving force in nature. Let me see if I can do one more. Okay, this is kind of a cool one. But that's a little, okay. It's a little tricky. So I'm gonna do this one. But I'm not gonna do the, actually I'll go ahead and do the whole thing. Okay. Now that's not an obvious way how to draw it, but remember, Alex is just asking you for the number of valence electrons, and I want to show you how to do that. So this one is in group 4A, hydrogen is in group 1A, and then nitrogen is in group 5A, okay? So there's 1 carbon, so that's 4. There's 3 hydrogens, so 3 times 1, and then there's 2 nitrogens, so 2 times 5. However, see how it's got a positive charge there? You subtract 1, lose 1 electron. Okay, right? Plus means you lost. Negative means you gained in terms of electrons. So I'm going to subtract 1. So the number of valence electrons is 4 plus 3, 7, plus 10 is 17, minus 1, 16 valence electrons. Okay, that's an important point. If this had been negative, you would add an electron. If it's -2, you would add 2 electrons. But since it's positive, that means you lost an electron. It's oxidized, right? It's oxidation when you lose electrons. And so you're going to subtract 1 for the total number of valence electrons. Now, the skeleton's not obvious here. It's actually not the same as it was with the oxygen. So I'm going to go ahead and draw the skeleton. So that would be difficult. If you see CH3, that's easy. It's just CH3. Then you see the N2. You might be tempted to say that the nitrogens are both surrounding the carbon, but it turns out this is a weird molecule. It's a weird ion. So it looks like that. Okay, so there's your skeleton. Now you can do the rest of the Lewis structure. We have the number of valence electrons, 16. We've already used 10. 2, 4, 6, 8, 10. So I'm going to subtract 10. So we got 6 electrons left. So carbon already has 8. Hydrogens have 2. So I'll put 6 over here. And now this nitrogen in the middle, which is a central atom, doesn't have enough. By the way, if it is charged, you want to put brackets and then put the charge outside of it. Okay? That's to tell us this whole thing has a positive charge. Now, how do we deal with the nitrogen in the center? It doesn't have 8, it only has 4. Carbon doesn't have any lone pairs, so it can't donate any lone pairs, but nitrogen on the end does. So I'm going to push a pair over. Now, what's that going to do? Okay, use this double-headed arrow. I'm going to draw this small. You now are closer to 8, right? Now you have a double bond there. But that that nitrogen in the center, it still doesn't have 8. It only has 6. So what do? You got to push another pair. Push one more. And now that'll give it 8. Isn't that cool? And that's what happens. You push these pairs until you get up to 8. And you get a triple bond. I'm sorry, that's so small. Okay, so you can push 2 pairs if you need them. If you need 2 pairs of electrons, push 2 to get that central atom up to 8. Now the nitrogen in the center has 8. This is all positively charged. This one still has 8 on the right. Okay, and the carbon has 8. And all the hydrogens have 2, so you're set. So I had to push 2 pair to get up to 8, but you can do that if it's necessary. That's called a triple bond on the right. Okay, the single bond here, but a triple bond here. 3 bonds between those 2 atoms. And there you go. Okay. Okay, I'm going to move on to this type of structure. So let me stop share. I'm going to show you these problems. There's a type of problem they have you do where you do diatomics, but the diatomics are easy. Let's not worry about the diatomics for now. These ones are a little more challenging. So this is drawing the Lewis structures for simple organic compounds. Okay, so now we're going to do the same thing that I was just working on. These ones are a little easier. The reason that last one was so difficult was because they were really just asking you for the number of valence electrons, but I went through the whole stages of getting the Lewis structure just to show you practice. Okay. So this one says, draw the Lewis structure for acetylene, which is C2H2. Be sure to include any lone pairs. Okay. When you draw Lewis structures, they have to have lone pairs if there are any. If there are lone pairs, you got to draw them in. Okay. So C2H2. This one's going to be a lot easier. Okay, so you have 2 carbons, so draw the carbons together. Remember, carbons are the trunk of a tree. The hydrogens and the chlorines and the fluorines, those are going to be the branches. So you got, the question now is, where do you put the hydrogens? If you have an even number of hydrogens, just draw them symmetrically. Put 1 on each carbon. There's a lot of symmetry in nature. Okay. Now let's count up that's the skeleton. Let me make sure these are lines. That's a pair of electrons. Each line is a pair of electrons. I didn't draw it very straight, right? Let me draw it a little straighter. Okay, now let's count up valence electrons. Carbons in 4A, hydrogens in 1A. Okay, so 2 times 4, 2 times 1. 10. We've already used 6, so we only have 4. So it's your choice. You can put 2 on each carbon if you want. I like to put them on opposite sides like that. Or you could do 2 pair on 1 carbon. It really, you'll get the same answer. I mean, it's, what are you going to do, right? Okay, so now we need each carbon to have 8. So I'm going to push a pair over. That's going to give each carbon 6. Let me show you what I mean by that. Let me space this out. I'm sorry. Right? Just push the pair over. But that only gives each carbon 6. So what are we going to do? Push another pair over. And there we go. Now each carbon has 8. That's called a triple bond. The triple bond is typically very strong. Okay. It has 3 pairs of electrons holding those 2 atoms together. Okay. That one's a little easier. Now, suppose that I had done it slightly differently. Suppose I'd said, hey, at this stage, I'm going to put both lone pairs on one of the carbons and none on the other. That's perfectly fine, because you're going to have to do the same thing. You're going to have to, in the end, get them up to 8. Right? So now we've got them up to 6, so we're going to have to push another pair. This is just an alternate way of doing it. There you go. So you end up with the same answer, right? These are equivalent to each other. There you go. Okay, let me show you another one here. This one, they want you to draw the Lewis structure for vinyl iodide. And vinyl iodide is C2H3I. Okay, a little tricky here, This one actually is not so simple. So again, think of it like a tree. You put the carbons together like a trunk. And then everything else goes off on the side. So it's not obvious where you put these hydrogens and iodines. We're going to have to put the iodine on one of them. So I'll just put the one on the right. It's okay if you put it on the one on the left. That's perfectly fine too. But here's the thing. We know that we have 3 hydrogens. So the question is, where do those hydrogens go? So it's your choice. What I'm going to do is I'm going to start with the idea they're all over here. Okay, maybe they're all over here on the right side. Now that may not be right. There's other possibilities. Maybe 2 of them are on the left carbon and 1 is on the right. Maybe 1's on the left and 2 are on the right. Maybe all 3 are on the right, although you can pretty quickly show that that wouldn't be right. That wouldn't be correct. So let's do it like that. So let's just see if this works out. I'm going to count up the valence electrons. You have 2 carbons, 3 hydrogens, and 1 iodine. So 2 times 4, right? Carbon is in group 4A, hydrogen is in group 1A, and then iodine is in group 7A. So that's a 7. So 8 plus 10 is 28. Is that right? 8 plus 10. We've already used 10. So we got 18. Got to get everything up to 8. So 2, 4, 6. Okay, let me see here. Did I do the arithmetic right? 8. I'm sorry, this is 18. Minus 10 is 8. I had way too many electrons. I knew that there was some arithmetic wrong there. Okay, so 2, 4, 6, 8. Right? 2, 4, 6, 8. So minus 8, we're down, we're out of electrons. So not too bad, right? If you think about it, the carbon in the center has 6 electrons. So I could push a pair over here, and that would give me something that actually works out technically. Okay, now we have a double bond there. So actually each atom, they all have 8 electrons except the hydrogen. That looks pretty good. Now I'm going to tell you this is incorrect. Even though we followed all the rules. Everything has 8 except for hydrogen, which has 2. The problem here is the lone pair. And what we find in nature is carbon very rarely has lone pairs. Very rare. It does not typically happen. So somehow we have to arrange this in such a way that the carbon does not have a lone pair, but it's not obvious how you do that. So here's what I'm going to do. I'm going to do an alternative. Here's what you do. You have 2 carbons and 1 iodine, but you got 3 hydrogens. It turns out that if you put a hydrogen on the central carbon, okay, that carbon on the right, that will most likely resolve the issue of a lone pair. So I did it. So here's what you're going to do. It's an organic compound. If you put 3 hydrogens on the left and none on the central carbon, you end up with a lone pair on carbon. The key here is to say, hey, no lone pairs on the carbon. We don't want any lone pairs. So if that didn't work and you can only get a lone pair, then put a hydrogen on the, move one of the hydrogens over. Okay, so that's what I just did. I moved one of the hydrogens over. That will most likely resolve the issue. You've got 18 electrons. We've already used 10. So that gives us 8 remaining. So same thing, put 3 lone pairs on the iodine to get it up to 8, and then 1 lone pair on that carbon. Okay, this is going to work now. Because now if you take a look at it, the carbon in the center has 8, but the one on the left only has 6. So what do? We push a pair over. So that's why this works. You get rid of the lone pair and you form a double bond. Now every atom, with the exception of hydrogen, has 8 electrons, but there's no lone pairs on carbon. Okay, so for any compound which is a simple organic compound, you want to have a final structure that has no lone pairs on carbon. And so that may require you to shift a hydrogen over from one of the carbons to the other. But if you end up with a lone pair on carbon, you know that structure is not correct in terms of these arrangements. Okay, let's see what we got here. That one's an easy one. Yeah, that's about as hard as it gets. Okay. All right. Now, what I want to do is move on to section 8.6, which is called formal charge. Now, this actually could have helped us in the previous examples. It actually can help you in terms of arrangements of atoms. Okay, so let's go through it. First, what I'm going to do is I'm going to show you how to do the calculation of formal charge. Unfortunately, there's no symbol for it, so I'm just going to write it as FC for formal charge as an abbreviation. Okay. Here's how you deal with formal charge. First of all, it's a type of calculation. It's something you calculate. And what we're looking for, the desired values are 0. We're looking for a value of 0 if possible. So here's how you do it. Step 1, you draw the Lewis structure. So you just draw a Lewis structure like we have. Step 2, you calculate the formal charge for each atom. Okay, every atom in the structure. If they just say, just do it for the carbon, you just do it for the carbon. If they say do it for the oxygen, but you do it for that one. But you can do it for every atom in the molecule, in the structure, okay? Now here's how you calculate it. You take the number of valence electrons for the atom. So you take that number. How do you get that? From the periodic table. If it's oxygen, it's in group 6A, so that's 6. If it's carbon, it's in group 4A, so that's 4. So you take that number, you write it down. Step 2, you subtract. You subtract 2 electrons for each lone pair. And you subtract 1 electron for each bond. Okay? Let me show you an example. Here's a Lewis structure for water. Okay? So let's calculate its formal charge. You look up how many valence electrons that atom has based on the position in the periodic table. Oxygen is in group 6A, so that's 6. Then you subtract off 2 electrons for every lone pair. Well, the oxygen has 2 lone pairs, so you subtract off 4. Then you subtract 1 electron for every bond. It has 2 bonds, so you subtract 2. And that is equal to 0. And that's what we're looking for. If you get a value of 0, that's very good evidence, or that is evidence that you've drawn a good Lewis structure. Okay? The formal charge is used, to evaluate Lewis structures. Much in the same way that the octet rule is used, right? Remember, with all these Lewis structures, we're trying to get these elements up to 8 electrons. That's the octet rule. If it only came out to 6, we'd say, hey, that's not a good Lewis structure. We got to do something. We got to change it. Same thing here. The formal charge is a way to evaluate the quality of the Lewis structure. So if you get 0, that's a good thing. Okay? Now, it's not always 0. We can have Lewis structures where they're not 0. But the smaller the value, the closer to 0. So formal charge values closer to 0 are evidence of good Lewis structures. Okay, the further they are from 0, the worse. So if you get +2 or -2, that's probably not a very good Lewis structure. If you get +3 or -3, it's definitely going to be a bad Lewis structure. Close to 0. Sometimes +1, sometimes -1. Those could be okay, but closer to 0. Okay, 0 is the best. Here's another example. Let's evaluate the formal charge for carbon, just for carbon. Carbon is in group 4A, so it has 4 valence electrons. It doesn't have any lone pairs, so we're not going to subtract anything there. That's a 0. But it has 4 bonds, 1 electron for each bond. Remember, a lone pair you subtract 2, a bond you subtract 1. So 4 minus 4 is 0. So the formal charge of carbon is 0, and that's a good thing. That's what we're looking for. The closer you can get to 0, the better. Hydrogen, you'd actually get 0 too, right? Because hydrogen is in group 1A, so it has 1 valence electron. It doesn't have any lone pairs, and it has 1 bond, so you get 0 there. So all the hydrogens have formal charges of 0 there. Okay. If you have an ion, at least one atom is going to have a formal charge that is not 0. Because it turns out if you add up all the formal charges of all the atoms, they have to add up to the charge of the species. So the case of water, they have to add up to 0 because water is neutral. But for an ion, they have to add up to the charge of the ion. Okay, so sometimes you will have formal charges that are not equal to 0. So let me show you one here. Okay, this is a good one to try. Okay, you're gonna write the Lewis structure. This one is a no octet rule. We're gonna get into the breaking the octet rule a little bit later. But I'm gonna show you the Lewis structure here, and then we're gonna evaluate the formal charge here, okay? PCl5, I'm sorry, PCl4 plus. Okay, let me show you what happens here. This is an interesting molecule or ion. Okay, we're actually going to let's take a look at it. Phosphorus is the central atom, 4 chlorine atoms. Those are going to be the surrounding atoms. So P, there's 4 of them, 4 of the surrounding atoms. So we can just write it like this. I could have sworn it said non-octet. This is a no octet rule exception. Okay. Well, we'll see. Okay, so let's go through. Phosphorus has 5 valence electrons because it's in group 5A. Chlorine has 7 valence electrons because it's in group 7A. So let's add up all these electrons. 5, 4 times 7, right? Each chlorine has 7, but now it's plus, so we're going to subtract 1. And that's going to be 28 plus 4, 32. We've already drawn in 8, so that gives us 24. Looking good, right? 24 electrons. Now, let's get the surrounding atoms, distribute them around the surrounding atoms until you run out of electrons. If you still have electrons left over, put them on the central atom. That's 24. That's 0, right? So now you're down to 0 electrons. Remember, when you draw a Lewis structure, you want to have brackets, and then you put the charge outside the brackets on the right side, okay? Some people will just do 1/2 a bracket, so they'll just put it on the right side with the charge. Sometimes people put it on both. I prefer both. Okay, so now let's evaluate this in terms of the octet rule. Every atom in that structure has 8 electrons, right? They all have 8 electrons. The chlorines have 8, the phosphorus has 8. So that's all octet rules. So I'm not sure why this particular problem, they say non-octet, because this is an octet. Everything is 8 electrons. But now let's do formal charge. And I'm just going to do it for 2 of the atoms. I'm going to do it for the phosphorus first, Fc for phosphorus. So phosphorus is in group 5A, so it has 5 valence electrons. It doesn't have any lone pairs, so don't subtract any there, but it has 4 bonds. So notice you get +1. With formal charge, you definitely want to put, it's like oxidation number. You want to put the symbol for the positive, the sign, +1 or -1, and you put the sign first, okay? So phosphorus is +1. Let's do one of the chlorines. Doesn't matter which one you pick, they're all going to be the same. I'm just going to pick this one over here. So chlorine is in group 7A. You subtract off 3 lone pairs, so that's 6, right? Each lone pair counts as 2, and then it's got 1 bond, so you get 0. So sometimes people will put the charges like this. They'll put +1 there, and they'll put a 0 there. These are all going to be 0. The chlorines are all going to be 0, right? Because they all have 3 lone pairs and 1 single bond, and they're all in group 7A. So actually, that looks good. Remember what I said at the beginning? Not at the beginning, just a few moments ago, that if you add up all the formal charges, they should add up to the charge. Here's what you get. +1 for the phosphorus, 0 for each of the chlorines. So you get +1, and that is actually equal to the charge. So you're set there. So I'm just not sure why they say this is a non-octet. 1 central atom and no exception, okay. It's not an exception to the octet rule. Okay, so I see what they're saying. I'm sorry. Let me share this screen. Sometimes it's the wording. So writing the Lewis structure for a molecule, this is, by the way, an ion, one central atom, which was the phosphorus, and no octet rule exceptions, meaning there aren't any exceptions to the octet rule here. So each chlorine had 8 electrons, as did the phosphorus, okay? Tomorrow we'll get into exceptions on the octet rule, okay? All right, let me show one more. We'll try one more of these. That's an interesting one. Okay, writing Lewis structures for a molecule with one central atom and no octet rule exceptions. Okay, same idea. This one's OCN minus. Okay. I'm not even sure what the name of that ion is. OCN minus. So see how there's 3 atoms? It's not like O2CN2, it's just OCN, so 3 atoms. So if you just have like 3 atoms like HCN or NaCN, you just draw them in a row. Just draw those 3 in a row. Okay, so OCN minus. And then I'm going to draw the group number above so that we can count up electrons, right? So how many do we have? How many valence electrons? Oxygen has 6, carbon has 4, nitrogen has 5, and it's negative. So we add 1 more. Okay, now let's draw the skeleton, OCN. This is definitely going to have like some multiple bonds. Okay. In fact, since it's charged, let's just get the formatting out of the way. We've already used 4, right? These 2 here and those 2 there. So that's minus 4 is 12. Okay, so now, like I said before, if you have these electrons, put them on the surrounding atoms first in pairs till the surrounding atoms are up to 8. Does that look good? So now I've used 12 and you're down to 0. Okay. Now the carbon obviously needs more. So now you have some interesting possibilities. You have 3 lone pairs on each surrounding atoms. So you could push a pair here. And I'm pushing that because that carbon only has 4 electrons. We need to get it up to 8. And that's going to get it a little closer, right? Now you have a double bond. Oops, I didn't want to show that. Okay, so we're closer. The carbon now has 6. So what are we going to do? So now you have a choice. You could take a pair on the left from the oxygen, or you could take a pair from the nitrogen. And that's actually comes up, that's an issue, like which ones do you do? So before I said if you had 3 lone pairs on one and 2 on the other, use the one that had 3 lone pairs to push a pair over. So let's use the same logic here. The nitrogen on the right has 3 lone pairs. The one on the oxygen has 2. So let's take one of these and push it over. It doesn't matter if you push this pair at the top or the bottom. Now, if you had used the oxygen, I'm not going to claim that's a wrong answer. You could probably do that too. That'll be an issue when we get into resonance. Some of these are kind of interesting structures they're giving us. Okay, so now, oh boy, that was a funny mistake. Now the carbon has 8, right? The reason we had to push 2 pairs is because it had 4. An extra pair gives it 6, so another pair gives it 8. They're all up to 8. Octet rule for everything. Now, what is going to be interesting about this is to do the formal charge. We're going to do the formal charge. I'm going to do it for every atom in the structure, oxygen, carbon, and nitrogen. So let's do oxygen first. Okay. So oxygen is in group 6A, so 6 valence electrons. It has 2 lone pairs, so we subtract off 4, and it has 2 bonds, so we subtract off 2. Remember, a bond is 1, and a lone pair is 2. The reason for that is a lone pair is only on that atom, so it gets to count both electrons. A bond is shared between 2 atoms, so each atom gets half of the bond, which is 1 electron each. So far, so good. Oxygen's at 0. That looks good. The formal charge is 0. Remember we said closer to 0 is better? However, they got to add up to the charge. So if the charge is -1, they got to add up to -1. So something is going to be -1. Let's do the carbon now. Carbon is in group 4A, so 4. It doesn't have any lone pairs, so 0, but it has 4 bonds, so that's 4, so you get 0. So far, so good. Okay. Oops. Now let's do the nitrogen. Nitrogen is group 5A. It has 2 lone pairs, and it has 2 bonds. -1. So there's our -1. I'm putting little parentheses around there, but we don't need to put parentheses. I'm just going to put a 0 there, a 0 there, and a -1. So that's not too bad. It does add up to -1. Now here's one little nuance. This is a detail. And that is the best Lewis structures have the negative formal charge. I guess I'm using capitals. On the more electronegative element. And remember the electronegativity values, 3.5, 2.5, and 3.0. So we might make a criticism of this Lewis structure. And the criticism would be that, yeah, we have 0, 0, which is good, and we have -1, so it adds up to -1. But we have the -1 on the less electronegative element. The most electronegative element is the oxygen. So a -1 on that one might be better, okay? So what I'm gonna do is I'm gonna show you how that would work out. Is there, and sometimes it doesn't work out. Sometimes there's just no best solution, but it turns out for this one, there is a good solution. How do we get -1 on the oxygen, but have them all add up to -1? That would mean the carbon and the oxygen would have to both be 0, right? If carbon and nitrogen are 0 and oxygen is -1, but still be octet. Is that possible? And it turns out it is possible, I think. And so what I'm going to do is this. I'm going to come back to where we were kind of in the middle there. So you remember I put 3 lone pairs on each of these 2 atoms? Okay. So here's how it works out. If I push 1 pair over here, I now have a double bond between the carbon and the nitrogen. We want this one to be -1. So what is it right now? What is the oxygen's formal charge now? I'm going to do a calculation on it right now just to show you. Okay, that's O, not 0. Well, it's in group 6A. It has 3 lone pairs and 1 bond, right? 6, 6, 1. Group 6A, subtract from that the 2 for each lone pair. 3 lone pairs is 6. Subtract 1 for each bond. 1 bond is, it already has a -1. It's already -1 right here. So that means we don't want to change it. So can we get an octet, but not change the oxygen? Right? Oxygen already has 8, so that's good. The carbon needs 2 more. So do this. Push 1 pair over there. And this turns out to work. Triple bond. Hey, now let's do the formal charge for the nitrogen. Group 5A, 1 lone pair, so subtract 2, 3 bonds, subtract 3, 0. So we got 0. Carbon is also 0. Let me show that for you. Group 4A, it's got no lone pairs, but 4 bonds, 0. Carbon's really cool, 0, -1. So there you go. They add up to -1, and the oxygen is -1 because it's the more electronegative element. Okay? And there you go. So that's actually a little better than the one where we had the double bond. And I want to show you this. If you want a formal charge of 0, for oxygen, it ends up being that if you have 2 bonds, that's going to give it a formal charge of 0. Those 2 structures will give 0 a formal charge of 0. If you wanted to have a formal charge of +1, I'm sorry, -1, I said minus, right? Then 1 bond and 3 lone pairs. Okay, so that's oxygen. Let's do nitrogen. So nitrogen gets a 0 formal charge when it has 3 bonds and a lone pair. So it could be like that, or a double bond and a single with a lone pair, or a triple bond and a lone pair. Okay, but in all 3 cases, when it has 3 bonds and a lone pair, it has a formal charge of 0. Okay, let's do fluorine. Fluorine is interesting. A formal charge of 0 is when it has 3 lone pairs and 1 bond. Okay, and then the last one is carbon. So let me do that over here. Okay, carbon has a formal charge of 0 when it has 4 bonds. Okay, now why is that? Because it turns out 4 minus 4 bonds is 4 minus 4, but no lone pairs, right? And so you could do that way, or you could do it with a double bond and 2 single, or a triple bond. I'm sorry, triple bond. And a single. Okay, so a double. You could also do it with 2 double bonds. So you see what, I keep putting in extra C's, sorry. You can see why carbon is an interesting element. It actually has 1, 2, 3, 4 different ways to get a formal charge of 0. And that ends up being the reason that it sort of acts like a trunk, is that there's just different arrangements of bonding it can have such that it has a formal charge of 0. Okay. And so I think, I'm not sure whether this helps people or not. Typically, they put this in organic chemistry. But it's often the case that, let me write it this way. So here's your element. So we'll start with carbon. Bonds, lone pair. Okay, this is to get a formal charge of 0. Okay, 4 bonds and no lone pairs. Nitrogen, I'm just doing like the important biological elements, the most important biological elements. 3 bonds and 1 lone pair. Oxygen, 2 bonds and 2 lone pairs. And then fluorine is 1 bond and 3 lone pairs. So see, there's a pattern there. 4, 3, 2, 1, 0, 1, 2, 3. Those are what will give them the formal charge of 0. Okay. Now, maybe this is helpful, maybe it's not, but let's do formal charge equals -1. And we'll do the same element, CNOF. Those are kind of the big 4 that we do. Okay. So -1 would be 3 bonds and 1 lone pair. And this would be 2 bonds and 2 lone pairs. And this would be 1 bond and 3 lone pairs. And 4 bonds. I'm sorry. 0 bonds and 4 lone pairs. Okay. So that's for formal charge of 0, of -1. Sorry. There we go. Okay. All right. Let's see. That pretty much ends section 8.6, Lewis structures and formal charge. So tomorrow, what we'll do is we'll look at resonance, and then we'll work on exceptions to the octet rule, and then we'll do bond enthalpy, and we should be wrapping that up, I would suspect, on Wednesday. Okay. So Wednesday, we'll probably finish up the last section. And then Thursday, what I'll do is I'll get a little jump start on chapter 9. Remember, chapter 9 is optional. It's extra credit. It counts just like the earlier chapters. So if you do it, you'll get credit just like you would for the earlier chapters, but you won't get penalized if you don't do it. But if you are going to take more chemistry, I would recommend doing the chapter 9. So I'll start on that on Thursday. And that'll give a jump start for the weekend because, you know, grades are due next week. So it'll give you the weekend to work on chapter 9, and then we'll go from there. Okay, so have a great day. This is sort of the last full week of classes. Monday is sort of the last meeting, and then Tuesday is the day of final exams. And so things are kind of coming to a head now. We're almost done there. You've gotten almost through it. So hang in there, okay? Bye-bye.